This is a video about black body radiation, and it's designed to help students who are studying for their astrophysics or cosmology part of their physics A-level specification. So in this image we're actually looking at something which is a pretty good approximation to a black body, which is a star. This is the star Vega. Vega's a really bright star in our night sky. You can see it without a telescope, you can see it with the naked eye. And it's the fifth brightest star, actually, about 25 light years away from us, so that when you look up at it and you see the light coming from it to your eye, it's taken about 25 years for the light to cross space to get to us. The surface of that star is thousands of Kelvin. It's about 9,600 Kelvin on the outer layers of that star, and it's the outer layers of the star that are producing the radiation that we see. And this is the reason why we study black body radiation, and we'll be applying our black body radiation theory to stars a bit later in this video. The first thing, however, is we need to look at the theory of black body radiation. And this was first come up with by Max Planck in about 1900. He actually had several unsuccessful attempts at it first, before he reluctantly used Maxwell and Boltzmann's graph and theory, which gets used for velocities of gas molecules in ideal gases. He used that theory to explain the light emission from bodies that are hot. And of course, by light emission, what we really mean is the photons that are coming from a body that is hot. So let's have a look at the graph. So axes first. So down on the x-axis, we've got the wavelength, and this is measured in nanometers times 10 to the power of minus 9. And up on the y-axis, we have the energy per second, so that's watts, over a particular area per meter squared, and we've actually normalized this graph a little bit with per meter as well, and that per meter refers down to the wavelength. So let's have a look at the top curve. This is a hot body, something that has a temperature of 7,000 Kelvin, and you can see that it has a range of different energies per second, a range of different intensities of photons produced across different wavelengths. So at its peak intensity, the peak, watts per meter squared, the peak intensity occurs at a wavelength of around 400 nanometers. And above that wavelength, so going through from the blue to the red end of the visible spectrum, we can see that the energy per second per meter squared drops, and it keeps dropping as we go up into the infrared region, and of course it would keep going down into the microwave and then the radio regions as well, which are off this graph. Going the other way from the peak, and now we're going up into the ultraviolet. This is a wavelength axis, so going down in wavelength means going up in frequency, and our graph drops down here. That isn't zero down here, there's still energy, but obviously not as much as, anywhere near as much as you have at the peak. And so it's this distribution, this graph, that Max Planck managed to predict after a bit of effort with some theory. And the important thing for us is that the graph depends on the temperature of the object, so that the cooler the object, you can see the graph now drops down here to 600 Kelvin. So its peak occurs at a different wavelength, and then 500 Kelvin, its peak at a different wavelength, etc. Okay. Now, interestingly enough, when we look at objects, we of course see them with our eyes. We see them as a combination of red, green, and blue parts of the spectrum. That's basically how our eyes work. So an object that covers all of these three regions, so an object, say at 6,000 Kelvin, would actually look fairly white to us because it's exciting the red part of our eye and the green part of our eye and the blue. And if all of those receptors are switched on, then we tend to see white. So we'll come back to that bit later on when we get you to do some work. So now let's apply that to the work of Wien. Wien characterized the relationship between the place where the peak occurs and the temperature. So here it is. We have Wien's displacement law, a constant 2.9 times 10 to the power of minus 3, divided by the temperature in Kelvin. It's really important that you remember that's in Kelvin, not Celsius or degrees centigrade. And when we do the 2.9 times 10 to the minus 3 constant divided by our Kelvin, we get the wavelength at which the maximum intensity of radiation is produced by that body. Now, if that isn't a mouthful, I don't know what is. So the interesting thing about this is that when we would normally write lambda max, we would mean the maximum lambda. That's how we normally write things in mathematics. But that's not what it means here, and it's really important to understand the difference. In this notation, we don't mean the maximum lambda. After all, maximum lambda would be off this graph. Okay, you can see we're not yet at the maximum value of lambda at which we get radiation. That's not what this means at all. What this means is the lambda at which we get maximum energy per second per meter squared. Okay, so the peak. So now we can apply this to stars. So here is the stellar spectra measured by astronomers of our star in black, and then another one for a nearby star, Proxima Centauri, about 4 light years away, and that's the brown curve here. So these two curves approximate a black body. That is to say that these bodies are hot and they're in space and they're in thermal equilibrium, so the amount of energy that they are producing through their fusion reactions inside the star is more or less equal to the amount of energy they're losing into space by radiation. So when the energy in equals the energy out, that means we are in equilibrium and the temperature isn't changing. And that's the kind of object that black bodies refer to. So we could use Wien's displacement law because we could go to the peak here, we could draw a line down onto the x-axis, estimate the wavelength down here, do the same for Proxima Centauri, find the peak, I reckon it's somewhere around there, draw the line down, find the wavelength, make sure we remember that it's nanometers times 10 to the power of minus 9, pop it into our Wien's displacement law, rearrange and find the value of the temperature for the layers of that star, the outer layers of that star that are producing that radiation that we're seeing. And that is what I would like you to do next. So find the wavelength for the peak intensity for the Sun and for Proxima Centauri using the last slide. Then use Wien's displacement law to calculate the temperature of the surface of these stars, and use the internet to research your answers and find out more about these interesting stellar objects, including trying to validate the temperature that you just got from the Wien's displacement law. Oh, and by the way, while you're there, why don't you find a picture of the Sun, our star, taken from space, just to check that it's really a real colour, really is white and not yellow. Okay, so a picture taken from the International Space Station or something like that would be great. Okay, I'm going to move on and show you my answers now. Here we go. So I did that exercise, drew those lines down, found the wavelength at which the maximum intensity of radiation was produced. There they are, 490 nanometers times 10 to the minus 9 for our star, the Sun. Popped it into Wien's displacement law, and out comes a temperature of getting on for 6,000 Kelvin, 5,900 Kelvin. Okay, something like that. Your answers are going to be approximate, and I've rounded this to 2 significant figures because the amount of data that I have going in is no better than 2 significant figures. And arguably we might even only be able to do 1 depending on the kind of screen you're trying to do this on. So if you're on a phone screen, you might be struggling to get anywhere near this number. So here then for Proxima Centauri, I estimated about 960 nanometers. I popped it into Wien's displacement law, and 3000 Kelvin was what I got coming out as the surface temperature of that star. Remember that the stars are much, much hotter than this inside their fusion cores, where the nuclear fusion of hydrogen is keeping them as a main sequence star. But by the time that we get out to the outer layers of the star, and we're producing radiation from those outer layers, and that's what we see, this star is considerably cooler. So that's the whole point of the video done, with a few extra bits and pieces for you to have a look at. And if you look very carefully at this image back on black-body radiation, you'll see an awful lot of other features of taking photographs of objects, and you might want to have a think about some of those as well. For instance, are the stars being taken as circles? Look at some of those in the background and tell me whether you think they're circular, and then think about why that might be or why that might not be. And then also these spikes coming from the star, okay? And have a think about why they might be. And I'll give you a clue. It's got nothing to do with the star. It's got everything to do with how we measure. So a nice little bit of extra bits and pieces for you to go in and have a think about.